Now let's talk about if the force is not constant. So a lot of examples in real life, when a force is applied to an object, it's not going to be a constant force. And so work done by a variable force, so the force might be changing as the object is being acted upon. And we're specifically going to look along a line. So the object is being moved along a line. So the work in this case, the formula is a little different than our last formula. The work is the integral of f of x dx from a to b, and this is where f of x represents the variable force. So this is the force acting on our object, and then this is the force moving our object along the x-axis, so our straight line, and this is from a to b, so from x equals a until x equals b. The other thing I want to mention before we do our next example is Hooke's law, because variable forces come up when you're dealing with springs. So over here for Hooke's law for a spring says that the force is equal to k times x, okay? And so you can translate this equation by the following. You could say force, or the force required to stretch or compress a spring, however much you want to stretch it or compress it, so x units from its natural length, is proportional to x. K is the force constant, or sometimes spring is what you'll hear, constant. Okay, so force is some value times how much you're moving the spring. So I have our formulas here for work and then Hooke's law. Now let's read this example and then go through it. A spring has a natural length of 1 meter. Okay, so at rest, the spring is 1 meter long. A force of 24 newtons holds the spring stretched to a total of length of 1.8 meters. So real quick, let's think about this. A force is applied to the spring and it's stretching the spring longer than its original natural length. Notice it's longer, 1.8 meters. So that's how much force is needed to stretch it 1.8 meters. How much work will it take to stretch the spring 2 meters beyond its natural length? How far will a 45 Newton force stretch the spring? So we're asked two different things here. Let's address them one at a time. Let's see what we need to figure out. The question is about work, okay? And to use work, I need my force equation or function. And if you look back at what we know, we do know how much force was required to stretch our spring 1.8 meters long, but we're asked about 2 meters. So this given information is actually going to help us figure out this force constant. So that's actually the first thing we have to do. So our first step is really to find the force constant or spring constant. Alright, so we're going to solve for K with what we know. We know that the force, 24 newtons, required to stretch the spring to a total length of 1.8 meters, is the force required to stretch to 1.8 meters. Now be careful here. X is not 1.8 meters. It says a total length of 1.8, but originally the spring was already a meter long. So you have to do subtraction here. So X, from our Hooke's law, X is how much the spring was stretched from its natural length. So you take, in this case, you can just do absolute value actually just to make it consistent. You can say originally it was 1 meter long, but we stretched it to 1.8 meters, and that's going to give us how much we actually stretched the spring away from its natural length. And so we have 24 newtons equals K times 0.8, because I just use absolute value. That way it doesn't matter which way you do this subtraction, that you keep this positive. Let's go ahead and divide this out. And this is meters, by the way, over here. And so we get K, if you just divide 24 by 0.8, is 30. So 30 newtons divided by meters. Okay, this is not joules, this is not the work. Newtons times meters is joules. This is actually newtons divided by meters. So this is our spring constant, or force constant. So we're going to use that in our formula for force. So let's go ahead and bring that in now. I'll go ahead and say that's our second step. So second, let's find the force And we know that F is K times X. In this case, we know what K is. So F is 30 times X. Okay. Now that we know what our force function is, we can go ahead and plug it into our integral to find work. Okay, so this was kind of our background information to be able to go to what's the question really asking, work. So now we'll say, I guess, third, we're ready to find the work, calculate the work. And we know that work equals the integral. Now, leave the limits of integration off for just a second. Let's plug in what F is. Integral of 30x dx. Okay, so our limits of integration, let me write these numbers and then explain them. From x equals 0 until x equals 2. Okay, because of how this is worded, it says, how much work will it take to stretch the spring 2 meters beyond its natural length? So natural length would be it's not stretched at all or compressed at all. So x is 0. It's not stretched or compressed. But it's stretched now beyond that by 2 meters. So that's why x goes from 0 to 2. Okay. And then this is super easy. Now that we have it set up, this integral is very easy for us to find. So let's go ahead and knock this out. This is 30x squared over 2, evaluated from 0 to 2, and 15x squared from 0 to 2, and we get that this is going to be 60. And then think about our units. We had newtons and meters. I didn't work it all out as far as leaving my units on here, but this is going to end up being joules. Okay, so it takes 60 joules of work to stretch this spring 2 meters beyond its natural length. Now, let's keep going because there's a second part to this question. How far will a 45 Newton force stretch the spring? So this time we know the force being applied is 45 newtons, but we want to know how far it stretched. What's that length? So for this last part of the question, we can actually just go back to right here. We have this nice formula we came up with for force because it says if this is our force, what's how far, what's the distance? So translate that as like a length or distance. So we're just going to plug right into our force formula. So I'll go ahead and do it up here. We know that the force is 45 newtons. This is equal to 30 times x. And then we just, and remember 30 is newtons divided by meters. Okay, and then x is going to give us meters because it is a distance. So then we just solve for x and we end up getting 1.5 meters. Okay, so how far will a 45 Newton force stretch the spring? We will stretch it 1.5 meters from its natural length. I'm going to show you one more example in the next video and then give you a handful of formulas that might be useful when you're working with these concepts of work and fluid forces.